Welcome to the garden. Today we're going to have a quick talk about how heat pumps, fridges work, and we're only going to cover everything because if we did, we'd be here for a month of Sundays. But first thing to say is that we are talking today about heat pumps, and by heat pumps we mean anything including your fridge, freezer that lives in your house somewhere, because it pumps heat out of the fridge and puts it into your kitchen. And we're talking about aircon that you might have in your office, at work, or if you're not in the UK and you're in America, you've probably already got air conditioning. Not common in Europe. Common in European hotels, but not domestically, I don't think. We're talking about great big industrial plants. This is also a heat pump because it pumps heat from the inside of the cold store to the outside of the cold store and leaves it in the air. That's a heat pump. And if you're talking about your heat pump water heater, that's also a heat pump because it pumps heat from the air outside and puts it into the water that then circulates around your house. So these are all heat pumps, and when we say heat pump, specifically we're talking about everything that works with a I will say vapor compression system, because it kind of is, and direct expansion, which is a specific type of system. And we'll go through, well, we won't cover what these mean specifically, but you'll get it by the end of it. But all of these are the same things. Within the industry, heat pumps refer to a specific thing. It's a reversible air conditioner. Fridge, freezers are specific things. Industrials are specific type. Heat pump water heater is specific. Display cases, all the rest of it. There's one of those things. The more into it you are, the more words there are for it. Kind of like the Inuits apparently have hundreds of words for different sorts of snow, but to them it probably makes a difference. To you, this doesn't make a difference, and it's a heat pump. Moves heat from A to B. Now, how does temperature, energy flow from A to B? Well, typically most people think, oh, it's kind of like water, the temperature flows downhill, kind of like water does, so it goes from the high temperature to the low temperature, which is true. If you have a hot body and you place it next to a cold body, energy flows from the hot body to the cold body. You've got hot, cold, and the energy flow goes this way until these end up at the same temperature, where T1 equals T2. However, that is not the main, okay, kind of is, but that's not specifically the way that we move heat from A to B with a heat pump. We use the temperature difference between the refrigerant and the air to get flow from the air that you're trying to cool into the refrigerant, and then we use the same difference between the refrigerant temperature being above the ambient temperature to reject the heat. So we do use that, but the main source of energy transfer, if you will, on this, or where it actually goes, is latent heat, and we'll probably do a video on this because it's again, it's a large subject. But what you have, if you have T here, and we'll call this energy here. If you have something like water that we're all familiar with, and the joy of water is that you've seen it in both a liquid and a vapor state. And you get the liquid water that you put in the saucepan, you turn the heat on, and then at some point you get steam coming off it, which is vapor. Now what happens is you put your water in at tap temperature, 15 in the UK, you put it on the stove, you turn it on, and you put in energy, and the temperature increases. And this, if you're at sea level-ish, 1 atmosphere, is 100 degrees C. But then, if you keep on putting energy into it, it doesn't get any hotter. It goes like that. And then when you've got all the liquid, here's liquid, and this is all vapor. And for a closed system, which is something you won't be familiar with, but that's what you have in a refrigeration system, you get all of it into vapour, and then the temperature starts going up again. And this bit is latent heat. It's energy that you put in that goes towards not increasing the temperature of the substance, but in the case of the refrigerant and the liquid water we're thinking of here, this goes towards breaking the bonds to evaporate the water. So you've got all your water molecules held together. They've all got quite tight bonds between them. And you kind of have to imagine it's like you're shaking it up enough to break all those bonds, which then frees the individual molecules to float away as vapour, because vapours are much further apart and less dense than the liquid is. By way of example about how this works with pressure as well, if you're on Everest, sea surface or sea level, let's put sea level because Everest is still on the surface, and this is going to be T Everest. Here, where your water boils at 100 degrees C on the surface, the corresponding point at the top of Everest is, from memory, it's about 71 degrees C, low 70s. I can't remember what. There's a difference between base camp and the summit, obviously. Low 70s. So what this means is there's a relationship between temperature and pressure. And the lower the pressure is, i.e. sea level 101.325 kilopascals, 1 atmosphere, when you go up Everest, the pressure is less, so there's less force pressing the molecules together. So it's easier to put in enough energy. You still put the same energy in, but it happens at a lower temperature because there's less holding it together. One way to think of it. It's not quite right, but it is sort of indicative and helps you to work out what's going on. At least get the basics of it before you go any further. So, the other board rubber's all the way over there. I'll suffer it. Let's think about boiling water just to show the effect of latent heat. So if you do this in your saucepan, your T start equals about 15 degrees C for most of the year in the UK. And your T end, TE, 100 degrees C. So your delta T in the pan is equal to 85 K, i.e. 100 minus 15. And the energy for this is, we'll say it's 1 litre, so 1 kilogram of water. So the energy is CP, oops, ignore that dot, CPM delta T, which is 4.2 kilojoules per kilogram per Kelvin, times 1 times 85. And when I put the numbers in, 4.2 times, I hope that didn't say boobies or anything when I first turned that on, or had some important calculation on, is equal to 357 kilojoules of energy, which is to heat the water from 15 to 100 degrees C. Now, we'll call it delta H, the enthalpy vaporization, is 2256. Oh, done that wrong, mate. Put the decimal place in the wrong place. 2256.4. The 4 doesn't matter. It's such a small amount compared to 2256, we can ignore it. 2256, and for 1 kilogram, again, that's 2256 kilojoules. And if we work that out, 2256 divided by 357 is equal to 6.3. So delta H equals 6.3 times delta E for this. So it requires 6.3 times more energy to break all the bonds without even increasing the temperature of the water at 100, or the boiling point, because we're using water, which is 100, than it does to increase the energy from 15 to 85. So what that means is, this is the useful part when you're thinking of refrigeration. And the temperature change useful for certain things isn't a huge amount. However, you do require energy, or you do require temperature difference to get energy flow, because if you rearrange this, you can see that delta E, i.e. energy change, is proportional to delta T, temperature change. So without having the difference, you would have no energy flow, because T1 would equal T2, and then there'd be no flow, i.e. like saying that the water at ground level is also next to the water at ground level. So it doesn't roll downhill. So this, of course, happens both ways. So when you condense vapour into water, you have to reject the 2256.4 kilojoules per kilogram for your water to condense it back, so that goes out to the atmosphere. So if we put this onto a fridge, we'll start here with a pump. And then we come out of the pump, high pressure vapour, and this goes into your condenser coil, and then comes out here as liquid, and goes into the opposite of your compressor, which is your expansion device, which goes from high pressure to low pressure. And then we come out of no manches. It's dark water, but this is refrigerant. We come out of the expansion valve as the low pressure liquid into the evaporator, and then we go through the evaporator, then we end up as vapour, and we go back to the compressor. Gonna need you, mate, because the blue one doesn't work. So, question is, how do you know what this pressure and this pressure is? Well, that depends on what system you've got. But your fridge at home in the UK, if it's recent-ish, you've probably got R600A, which is isobutane. Don't know what you've got elsewhere, but this is certainly very common in UK for fridges. If you've got an older fridge, you might have R134A in the UK. You might have some YF. I've seen a couple of them around. It's quite rare. Isobutane is very common. And all we can say here is that the food in your fridge, if we draw your fridge here, this is where your food lives. And this is going to be between, it's going to be between like 1 and 5 degrees C. Depends what you set it as, what you put the dial in, that no one's ever worked out which way it goes. Not important. It's going to be around 1 to 5 to keep your food fresh. So that means that your refrigerant in here, or the evaporation temperature, is going to be, because we need temperature difference, we'll say about 10K below it. So what we'll do is we'll set this at -8 degrees C, and this is the refrigerant that's in the pipes. Well, if we look at our PT table here, our isobutane, what we can see is that -8, and I don't like any of these units, but we're not using a gauge set, so we're using absolute, is 1.17, which is just over 1 atmosphere. So the P here equals 1.17 bar. And obviously when you design refrigeration systems, you take into account the temperatures you need on either side of it, a million other things, and then you select the right gas. So what about up here? Well, this bit's in your kitchen, which is everything that's not in your fridge. All this lives in your kitchen, and this is why if you open the fridge door, the whole room heats up, because you're cooling the room only to move the heat from the fridge to the outside of the room, and then add some more energy here, and the whole thing heats up. So what we've got now is this is 20 degrees. I mean, if you've seen your heating bill in the UK and you happen to be in winter at the minute when you're watching this, it might not be 20 degrees. Unless by the time we get to winter the prices come down and everything and everyone's rolling in it. Probably not. And again, I mean, I want 15 on the condensing side. But, I mean, yeah, let's just use, 35 isn't there. We'll use 10. 10, I've always liked 10. 30 degrees C, which is 10 degrees above the 20 degrees ambient, so we get some flow. In reality, it's going to come out of here quite a lot hotter than this, but that's what we need to get the energy flow at the latent condition, which is where all the energy is changed. Latent's much better for energy change than temperature change is. You can work that out. 4.05. So this P here is 4.05 bars. So now, what you've got, just from knowing roughly the temperatures and knowing which gas we're using, we've now managed to work out what temperature we need to evaporate. Well, that's evaporation. This is, and if we say T condensing, just to make it clear, is 30 degrees C. We've been able to say that we want the room temperature at a room is in refrigerated space temperature, bit above 0, -8 evaporating. With isobutane, that's 1.17 bar. The ambient temperature, i.e. everything, not the refrigerated space, 20 degrees, so we want to condense at 30 degrees, which with isobutane is 4.05, and then you size these components accordingly, and you work out the capacity, mass flow, all the rest of it, work out what you need. And essentially, that's all it is. And it really isn't that complicated. And there's a quick caveat to this. It's also not as easy as I just made it out to be. There's a huge amount of detail that goes into every single part of this, right? But as said, we'd be here for a very, very long time. But this is a quick-ish overview of how sort of your standard vapor compression, direct expansion refrigeration system works. Hopefully in terms that you're familiar with, and hopefully it's straightforward enough that you get the concept of it without knowing sort of all the really tiny details that you can build on later. But it's very similar to this. Oh, that's all she wrote.